Yeah. So for the people who tune in with the start of the recording, I just went over the spectrum of SupercheQ and how it does asymptotically. And I'm now going to dive into what SupercheQ does. And maybe for the recording, I'll just briefly say again that the task that we're solving is just checking if two files are the same, if Alice and Bob distributed data centers have the same file. Okay, cool. So I'm going to go on a slight tangent and talk about the generic protocol for both SupercheQ EE and SupercheQ IE. And it's actually not that complicated. So the generic protocol is that both Alice and Bob are going to take their file and map it to a quantum state, which is fingerprint. If they have the same file, it should be a deterministic mapping. So it's going to always map to the same fingerprint at the same file. And then the referee who's going to judge whether or not these two files are the same is going to receive the fingerprints and report whether they're the same quantum state or they're different. Now, quantum state discrimination is a very rich field of exploration, but in this case, we're going to be able to do fairly simple tests. You may be familiar with the swap test, which is one way of estimating inner products between two quantum states. Another example that we use is the destructive swap test, which I can talk about a little bit more later. But the key, and then there's many others. But the key point here is oftentimes state discrimination is hard. But in this case, we're always going to be in scenarios where the overlap between fingerprints is either exactly 100% because they're identical, or it's less than some constant like 50%. And that means that the number of repetitions you have to do this is logarithmic in the inverse error, which is perfectly good. But it does mean that we're going to have to run a few fingerprints to reach a certain level of confidence. Just one way to think about this that I found helpful is it's like imagine that I give you a coin that's either a real fair coin or it's always heads, totally biased. So how many coin flips would you have to do to figure out if they're which coin you got? As soon as you get a tails, you know it's a fair coin. But if you keep getting heads and you got 30 heads in a row, you can be pretty certain that you got the biased coin. So that's kind of what we do for distinguishing here. That's the tangent. Let me get back to SupercheQ EE and why it works. So the key insight and intuition for why this works is that Hilbert space is massive. I don't have to convince you guys of that. But it's in this context particularly massive in that Okay, yeah. So I was just explaining that there's this double exponential number of bins intuitively. And this, you've seen things like this before where you see the scaling of state vectors, but usually there's some catch where the actual quantum algorithm doesn't preserve this exponentiality, but here it does. And so now I'm going to talk about, this is why it works. I'm going to talk about how it works. So for the TikTok generation, I have a meme version of it, which is that in 2001, which is when the existence of quantum fingerprinting was first realized, the idea was that you would deterministically assign files to specific bins. But in the refined 2022 era, our approach is actually going to be to randomize the assignment of files to bins. And so let me explain what I mean. In the original quantum fingerprinting existence proof in 2001, the idea is that your first file goes into this bin, which I'll explain a little bit more. Second file goes here, third file goes here, fourth file goes here. And in general, you can fit, for 3 qubits, 256 files into the space. What we're going to do is just randomize the assignment. First file might go here, second, third, fourth, etc. And this might seem like a really bad idea because eventually you're going to get a collision. And a collision would be really bad. A collision would be that 2 files map to the same fingerprint. That would break the entire goal of what we're doing, which is to not have collisions. And you may be familiar with something called the birthday paradox. So these are the 24 astronauts who have been on the moon. And interestingly, 3 of them, 3 pairs share birthdays. And more broadly, you may have heard this fact that if you have a room of 23 people, which is approximately correct here-ish, there's likelihood more than 50% that 2 will share a birthday. And the key point here that this graph is making is that this is a quadratically scaling issue. It's a problem for hash tables, and there's a birthday attack. But in this case, it actually doesn't impact us negatively. Well, it does impact us square rootly negatively, but you're fighting against a square root disadvantage with an exponential advantage, and the exponential advantage just easily wins. So in this case, it doesn't matter that we're going to have square root less performance than the 2001 protocol or existence protocol, because you add 1 qubit and you are back to where you want to be. So now the problem is, how do we get assignments of files to random bins? And what I mean by random bins is different state vectors in Hilbert space that are all distinguishable. So the best thing we could do is true randomness, which is Haar randomness. And this is a theorem in our paper. It says that if we could Haar randomly draw, this is the double exponential, 1.4 raised to 2 raised to n qubit states, then there's essentially 0 probability in the n approaches infinite limit that any pair has fidelity exceeding 0.5 overlap squared. And if you're wondering if this limit is practical, it is. Even at like 5 qubits, it's basically 0 probability that within like heat-death universe lifetime that you would have any sort of overlaps greater than 0.5. So the reason that this occurs is that this is the probability distribution of the fidelities between randomly drawn states in n qubits. And it's something called a beta distribution. But this has an expectation value of 0.5 raised to n. But if you only tried to prove based on that, that wouldn't be good enough. And so on the bottom right, this is a figure about these results on Porter-Thomas distributions and anti-concentration, which you may have heard of. But the point that this is making is that if this left-hand side was the probability distribution of fidelities in 2 random states in Hilbert space, that it's always a delta function at 0.5 raised to n, that would not work for us. You could get that with just initializing a Hadamard superposition on both fingerprints, but that would not be good enough here. The reason this works is that the actual distribution is more like this. And in fact, this is it's a more extreme version of this, where yes, it's possible that you could have a high value because 2 fingerprints that are the same are 1.0. But because you have so much of your weight, more like 1 raised to 2 raised to 2 to the n, then on average, you're going to have basically your variances and third and fourth moments are going to keep you to always have low overlaps between random states. So essentially, the proof for this results from looking at the higher moments. Expectation value is the first moment of this probability distribution, variance the second moment, so forth. And the catch here, though, is that you do need a lot of gates for true Haar randomness. You can achieve it, but you need poly and N gates where this is capital N, the size of your file. So if you have that 100 petabyte file, that means you're going to need 100 peta gates, essentially. And that's a problem. So then we looked at, I would say the main theoretical contribution of our paper is something called an approximate unitary T-design. That's actually, that term is known, but using approximate unitary T-designs. So informally, an approximate unitary T-design is like pseudo randomness for the Haar measure. This is true randomness, but if we could approximate this randomness, then we can still do really well. And in particular, a T-design is a distribution that preserves the first T moments when you're comparing to Haar random sampling. So if you have a 1 design, you recover the expectation value. If you have a 2 design, you recover the variances, 3 design, et cetera. And what we show is that using these results on T designs, which can be formed in polynomial depth, if you want to get 1.4 raised to n raised to L, where L is a constant number of files that map to different spaces in Hilbert space, then you need a circuit that has this depth. So that still seems pretty gnarly, and I'll address that later. But the best that you can possibly do classically, and this is proven, is L equals 2, which is like a quadratic advantage that you get with classical fingerprinting. So if we did L equals 2.5 or L equals 3, then we would have scaling that's essentially n raised to 15 minus 4 is n to the 11th, which is polynomial. It's a horrible, horrible polynomial. But essentially what we're showing here is that with polynomial depth in the size of lowercase n, the size of your fingerprint, you can get fewer gates needed, and it's compatible also with nearest neighbor interactions. In fact, this is a 1D circuit model that produces sufficiently random fingerprints in Hilbert space. So you'll notice that this is a really horrible polynomial, though. If we want quantum advantage, which is L equals 2.01, you'd still need something like n to the 6 scaling in your circuit depth, and that's pretty bad. So what I want to point out is that our bounds are extremely loose here. We use these things called union bounds and Markov inequalities that we frankly didn't even try to optimize them that much, in part because the basic results on approximate unitary T-designs themselves have a huge gap between what's theoretically proven and what is actually conjectured to hold. In particular, if you want a T-design, it's the best result right now is that you need like T to the 5th depth, and that's where this 5 comes from. But it's conjectured that you only need linear depth, and it's not been proven, but every numerical simulation has shown it. So we just wanted to prove the polynomialness, but the practical variant of SupercheQ is just to disregard the loose theory bounds and just run it and see how it works. And what I mean by hardware efficient is that you should use whatever scrambling you have to your advantage. So we like your paper on the 3-qubit interactions for the itopically. That could be one way to scramble faster because you distribute entanglement faster. If you have Q tricks, and this refers to a paper that I'm working on with Gokhale and Noah and others, and Ravi and others, you can increase your Hilbert space even faster. So basically, anything that you can have to throw at your problem that can help scramble faster is a good thing. And you don't even need to know what the unitary you're implementing is to some level, as long as it's unitary. If it starts to become incoherent, then you have a problem. But if it's unitary, then you're good. So we simulated this, and I'm going to show some of the simulation results. We looked at ColdQuanta's hardware, which is a neutral atom quantum processor in a rectilinear gate layout or qubit layout. And one of the things on our hardware is that we have a global R gate, meaning that we have to do, it's both a curse and an opportunity. If we want to do Rx gates on any qubit, we have to do them all the qubits at the same time. So, but on the other hand, we get to do them pretty fast and without crosstalk. So that's these gates. Then we can do individual RZs in every qubit. And then we can do CZs between any pair, working on Rydberg interactions that are higher radius as well. So this is a circuit model that we looked at. And essentially, we did the following. We took several files, literally just bits, and we used those as seeds to a random number generator. And essentially, for each seed, we get angles for each of these values. And this is not neutral atom specific. It can work for any hardware, including yours. And so basically, each file has bits that map to a set of random angles that specify this quantum circuit. So this is how we simulated it. You're going to notice that we need high performance compute for this, or GPUs in this case. And the reason is that because SupercheQ is so efficient, if you want to make sure that all the files map to different places, you need the number of files, the number of state vectors M, to be pretty large, ideally double exponentially large in the number of qubits, to make sure that you have you've tested the Hilbert space fully. And then you have a quadratic on top of that because you need to compute pairwise overlaps across this double exponential, which is horrible scaling. And that's why we use GPU, both for getting the state vectors, assembling them into a matrix of the state vectors, and then essentially multiplying that matrix by its conjugate transpose to convert it to a heat map of overlaps between states. And so that was the GPU usage that NVIDIA helped us with. And these are the results. So I'm just going to focus on the purple lines. So purple is referring to taking a 9-qubit array and then stuffing it with 1,000 files, which is beyond the 512 limit of classical. And the dashed lines here, which I'll cluster together at the bottom, are basically if you had true random sampling, how much fidelity overlap would you have between distinct files? And these are averaged over 5 trials. And in the solid lines, it's reporting all 5 trials with error bars. And what you notice is that even in just depth of like 4 or 5 layers, you're visibly indistinguishable from randomness. There is still this exponential decay property, but it shows that essentially with just 4 or 5 layers, you can actually get pretty close to true randomness. And you can think of each of these lines as actually not just a trial, but a real protocol that produces fingerprints for files that all have very small overlap with each other. In this case, all are below 0.05, 5% overlap for depth 5. And that means if you run 3 copies of this, then you've suppressed the false positive result probability to 5% times 5% times 5%, which is really small. If you do 100 copies, there's just no chance of errors here. This is the same result for fully connected qubits. And the reason I show it is that there's basically not a difference. This is partly an artifact of the fact that with just a 3x3 qubit array, your entanglement spreads so fast that there's not really a difference between these two. And we would have liked to show this. What we wanted to make the point of is that actually, we're going to expect these results to hold in general, where there's not that much of a difference between limited connectivity and full connectivity, because the results on approximate designs, as long as you run enough that there can be entanglement spreading like a light cone from one end to the other end, you're good. And that's what 3 layers, 4 layers does in this array. Yeah.
You're going to repeat this, they can't hear me, but you know, approximately after step 5, what moment of design you're approximating?
Yeah, good question. So Gokhale is asking, after about depth 5, what moment of the design are we approximating? So based on our loose theory bounds, we're not even approximating the second moment until we get to like depth of 50 or something. But if you believe this conjecture of the scaling of T for T designs, it more or less means that you're already at the 5th moment after 5 layers. And we do believe that conjecture. Cool. So these are the noiseless simulation results. Noise does seem to probably kill this, but not entirely. So these are the same results with noise. And the only thing that I want to point out here, we simulated it under a few different noise models, is that there is this sweet spot where even with noise, as you add layers of depth, it still goes down initially for about 3 to 4 layers. And then eventually you're in trouble. It starts to go up because you just eventually approach the maximally mixed state, at which point no state is distinguishable from any others. But if you have certain noise models, go ahead. These are noise models. Yeah, this is not experimental. And this is like the heat map, essentially, of with these noise models, the heat map. So the one file is here on the x-axis, another file is on the x-axis and y-axis. The diagonal is comparing a file to itself. So if you compare a fingerprint to itself, you always get the same thing. But anything off diagonal is comparing 2 different files. And you see that there's a very clear separation between checking if a file is the same versus checking if it's a different file.
Is there a reason you chose to have your parent model be stochastic? You had you expect a difference in those two?
That's a really good question. I actually had the same question for the guy who did these simulations, and I don't think I've heard an answer back yet. This is Teague, I think, you know. To give you some sense, this paper really came together in like the last few days. So we're definitely gonna have some V2s, and I'll show you a mistake in one of my next slides. Skip over this, but this is just like another way to visualize the noise simulations. But one thing that's encouraging from this is that, well, you see that even at short depth, noiselessly, you get really good results. And here you see that at shallow depths, you still get some improvement before noise wipes out any advantages. And so we were motivated by that to try this experimentally. And we ran essentially this circuit on IBM hardware. So you can think of Q0, Q1, and Q2 as Alice, Q3, Q4, Q5 as Bob. And essentially we run a quantum volume experiment. So we pick a random SU4 unitary for these 2 qubits, a random SU4 unitary for these 2 qubits, and then Bob independently, who pretend that his qubits are very far away, does the same, but using the same random seed so that they have the same file, they pick the same random unitaries. And this could get repeated D times. Quantum volume experiment would be you do it D equals n number of qubits times. We actually just did it for D equals 1 to make it pretty shallow. So the rest of the circuit is something called a destructive swap test. And it's essentially trying to measure, after Alice and Bob have prepared a fingerprint for their file, let's check what the overlap is between their fingerprints. The destructive swap test has this nice property that if you have linear connectivity, like on your device too, then you can do a swap network with very low number of swaps to get essentially this pattern reads out the overlaps between the 2 states. So these are the experimental results. The mistake in this plot is we had a post-processing mess up in the scaling. We were wondering why are the fidelity, like we thought that if the fidelities are this low, attenuated that much, we expect attenuation, but if it was attenuated that much, we thought there shouldn't be a clear pattern on the diagonal. And it turns out that there's just a missing like factor of 10 or 100 or something here. But the left-hand side is the simulated results, noiseless. And as expected, when you compare a file to itself with the diagonal, it's 1.0. As soon as you step off the diagonal, it's 0.1, 0.2, et cetera. And when you do an experiment, which is the right-hand side on the Algiers 27-qubit device, you still see a very clear pattern on the diagonal. Again, ignore these actual numbers, but these are the fidelities, the histogram fidelities. So orange is when we compare distinct files, get their fingerprints and compare them to each other. And blue is where we have identical states. Ignoring the x-axis, which is much bigger separation in actuality, there's a clear separation between blue and orange. And although if we ran this for higher depth, it would start to converge, we're happy that we have some separation that's clear. So that is SupercheQ EE. And I'm going to switch gears into the next slide to talk about the incremental encoding. But I thought I'd pause here in case there's any questions here or on the chat. Check the chat.
Quick question here. So there's like an advantage to not doing true or random sampling. Does that tell you anything about the states that you're excluding? Are there like some special kind of edge states that you're not sampling? What do they represent?
Yeah, it's a good question, and I'll repeat it. Ravi's asking, we saw that when we do approximate random sampling, we still get good results, but it's still missing some corners of Hilbert space, so to speak. Can we say anything interesting about those corners that we're missing? Is that a fair recapitulation of your question? So T equals 1 and T equals 2 designs essentially are Clifford circuits. So one answer is that, and actually this motivates the next slide, we're going to find that Clifford circuits alone, so no T gates, nothing else, are sufficient to get one form of advantage. But clearly you're not exploring all of Hilbert space with just Clifford circuits. I don't think I have more intelligent thoughts on that otherwise. It just maybe at least at that T equals 2 to beyond, it's looking at what happens when you have T gates and when you don't have T gates. And it turns out without T gates, you can still do some interesting stuff.
That's one question. Yeah.
Sure. So question in the chat is, for experiment, use 20 qubits, right? How many shots were required for this result? We used a 27 qubit chip, but we only used 6 qubits of it. It's 3 plus 3. And in the destructive swap test, you don't need an in silo, so that's why it's not 7. And we used, I think, 10,000 shots for each experiment. Cool. Any other questions? All right, I'm going to switch gears now to talk about SupercheQ IE, which is the incremental encoding. And I want to motivate it by these 2 screenshots from, one is documentation again from Oracle's MySQL database, and it's a performance consideration about fingerprinting, about checksumming, which is that if you have a large database, every time that you produce a fingerprint, it takes a long time. And if you have a database that has only 1 or 2 read ports, you can actually take your entire database offline while you perform fingerprinting. And in fact, this is not just like a small thing that we found in the documentation. It's all over Stack Overflow and developer forums where unwitting users are like, oh, fingerprints, let me check some of my files to make sure they're good. It takes their database offline for minutes, hours, potentially days. And that's a problem. This is a Stack Overflow posting about it. So this is the setting that, okay, well, so that motivates us to wonder, what could we do to handle incrementality? So if you're just doing a classical fingerprint, then you have to recompute it every time your file changes. Imagine you have 100 petabytes and your Maxar satellite database, and you just decided to like change the copyright on one file. You don't want to go through 100 petabytes of information again. So that is what SupercheQ IE does. And I'm going to show how it works with an example. So let's say this is our data. It's 15 bits. What I'm going to do is write the data into the lower left triangle of a table. So I'm putting the first bit here, the purple in the next row, blue next row, orange, and other orange color, or brown and orange. I don't know colors. Okay, so this is our one representation of our database. And now I'm going to flip it over the diagonal so that it's a symmetric matrix. And you may recognize that this can be regarded as a adjacency matrix of a graph. And in particular, this is the graph that is represented by this adjacency matrix. Every vertex corresponds to a row, and you have an edge anytime there's a 1 in the row and column position. So essentially, you can represent any file by a graph that has approximately square root of 2n vertices. And classically, that wouldn't really help you because if you actually store this graph, you have to keep track of the edges, and that brings you back to the full file size. But quantumly, there's something we can do here. And as you can probably guess, we can take this graph and construct a graph state out of it. So a graph state is a quantum state that is stabilized by essentially the rows of that adjacency matrix. But that's the sort of theoretical way to look at it. A more practical way to look at it is that it's just a state that is formed by first uniform superposition, all Hadamard's, and then anytime there's a link between 2 nodes and the edge, you apply a controlled Z. So just to verify one example here, the first node is connected to the second, the last, and the penultimate. And you do see that there's CZ from 0 to 1, CZ from 0 to last, and CZ from 0 to penultimate, nothing else. So essentially what you can do is you can represent any file with a graph of size root n, technically size root 2n, and then convert that graph into a qubit graph state that has square root of 2n qubits. And why does that matter? Let me show you an example of a bit flip. So this is that file that I was describing, and we took a fingerprint of it, in this case, using this state. What if now the first bit of that file flips? So we go from a 1 here to a 0 here. That 1, which was this one, represents whether or not there's an edge between the first and the second qubit. And we can patch that up essentially by just having another CZ after the update is made, so that this edge is essentially unwritten. CZs commute with each other, these cancel out. And now you have a faithful representation of the updated data in your database. So that's basically all there is to it with SupercheQ IE. And the important fact is that all graph states that represent different graphs have different fidelities. At most, you have 50% fidelity, well, squared overlap between 2 distinct graph states. And of course, if you have the identical graph state, then you have 100% overlap between them. So that's SupercheQ IE in a nutshell. And maybe just to flash up both protocols on the screen. In SupercheQ EE, we showed that if Alice and Bob have capital N bits, they can check whether or not the files are the same by only transmitting as few as log n qubits. That's with true random sampling. But if they want lower circuit depth, they can do n raised to 1 over k qubits. K equals 2 would be classically the best you can do, square root of n. But you could do here k equals 10. You could do n to the 0.1 power. And it only takes time that's polynomial in k. And again, even that is not the best we can do, because if you believe conjectures about approximate unitary T designs, then you can get scrambling much faster than that. So that was SupercheQ EE. And SupercheQ IE was this idea that if we take our data and it changes, we have a bit flip, we can even support resizing the file. In that case, you just add a new qubit. Then you can transfer square root of n qubits by representing the graph state. And anytime your file changes, you can apply the CZs that you need to fix up, to flip the bits that you need to fix to have the updated fingerprint. And to our knowledge, it's the only incremental protocol for fingerprinting. And it's unlikely that there will ever be a classical incremental protocol based on various cryptographic papers. One more thing that I'll mention that I forgot to say about SupercheQ IE is that notice that everything here is a Clifford circuit, or Clifford gates. All you got is Hadamard's and CZs. And the swap test does require a controlled swap, which is non-Clifford. But if you do the destructive swap test, then it is Clifford again, which means that this entire circuit could be run without any T-gates, without any magic state distillation, fault-tolerant regime. And that's nice because as people start to think about protocols for early or applications for early error-corrected devices, if you don't want the 100x overhead of magic state distillation of T-gates, then we propose that this is one of the first things that may be interesting to run. So where could this go? Potential applications could include transaction consensus. So financial institutions, which you guys met a lot of at QTV, have this problem of having distributed data, and they want to make sure that the data that each node receives is the same. And especially if you have protocols for distributed data, that can be a problem. So that's an application that we perceive some interest in at QTV, the conference I was at yesterday. At a much more microscopic scale, I mentioned chip design. So a big reason for power consumption on a chip is when you have signals that cross cores or cross from one program register that's here to another program register that's here, that does cost electricity. And if we could reduce the amount of communication there, that could be valuable. I do realize how slightly ridiculous it sounds. The protocol that's being proposed is that in your CPU, you have QPUs inside, but bear with me one day. And then deduplication. So imagine your Dropbox, you have 2 servers that have a lot of shared files, and you have too much replication, you need to save some space. You could potentially use this to deduplicate, figure out which files are the same on both servers, and then get rid of those. And then copyright protection, tamper detection. This is where I mentioned that classical fingerprinting protocols are already used. If I download a file, some software, and I want to make sure that that file is not changed, antivirus uses this, then I can use fingerprints to keep track of that and have a history of that. We have also integrated SupercheQ into SuperStack. It's part of our Qiskit SuperStack and Search SuperStack APIs, which you guys should at AQT all have access to. And essentially, we have APIs that produce these random circuits under different models, have visualizations of the heat maps and the scalings, and work for very specific files, actually. Those are real files that we fingerprinted that were large. So my last slide is just key takeaways here are that we want to have this message that random circuit sampling, quantum volume, quantum supremacy, et cetera, actually does have at least one practical application. So to the extent that you hear these fancy announcements of some company coming out with a quantum computer that's doubled quantum volume, there is actually plausibly an application to that, which is pretty cool. And in fact, we're working right now to measure Q-trait quantum volume. So definitely a link here. What is the application? It's a up to exponential advantage for distributed data for a very generic task. For many applications, hashing is the right way to go. But anytime you're in an adversarial setting or a security constrained setting, this is the way that it should be done. And for AQT, I think my message would be that you can use experimental quirks or of your hardware to your advantage. Maybe quirk is not the right word here, more like features. So if you can do multi-qubit gates, that's a great thing. It spreads entanglement more rapidly. If you can do qubits, that means you're in a higher dimensional Hilbert space. So there's potential there. And yeah, the paper is on archive as of Wednesday night. And looking forward to taking any other questions. Yeah, this is a good question. So yes, it's fully classically simulable.
Could you repeat it?
Oh, yeah. So I was asked, SupercheQ IE is simulable because it's Clifford circuits. Does that mean that we could simulate this whole protocol, like run it classically? And part of the answer is like no, in the sense of like QKD is also classically simulable, but that doesn't mean that you can actually use like a classical simulation of it in an actual application. In this case, you would still need to have like the quantum states transmitted. And the incrementality is that you can only apply like one CZ and immediately flip everything. The broader point, though, is really interesting. So this paper actually, the history of this paper is that we first came up with SupercheQ IE. And then we were really happy. And then we found out that classically you can also do, and we were like, ah. And then we went out of Clifford subspace. But this is one of a sequence of 3 papers that Eric Anschutz, second author, the equal first author on this, worked on, that shows that even with Clifford circuits, you can get quantum advantages. And this is kind of surprising because theorists often talk about like, oh, Clifford circuit, easy to simulate. That's true, but it's still a quadratic separation in the sense that if you have the Clifford circuit with n qubits, you only need n qubits to simulate it, whereas to run it, whereas classically you need n squared stabilizers to measure it. And that's actually a quadratic advantage. It's the same as Grover search. Sometimes quadratic advantages are derided by certain people at Google. But in this case, if you don't have the error correction overhead of needing T-gates, that significantly makes it more plausible to run it with some quantum advantage. You may have seen this paper from Google called Focus Beyond Quadratic Speedups for Quantum Advantage. And they have a lot of good points in there, but it all assumes that you have a big overhead of T-gates and magic state isolation. In this paper, as well as Eric's previous 2 papers, there's no such overhead since it's all Clifford. It's a good question. Sure. So in the financial transaction consensus example, you can imagine that. So the best way to think about it is a scenario where there's a supplier of the files and the supplier wins some adversarial setting when they can supply 2 different files that map to the same fingerprint. So for example, if Alice stores a set of credit card transactions and Bob is a compromised node that is supposed to mirror that, if there's a supplier of files who can say, so I know that Alice received a transaction for this T on my credit card. If I can supply a alternative transaction to Bob that is saying that I made a payment for $40,000 to Best Buy to buy new Xboxes, then those, and she can do it in such a way, the supplier can do it in such a way that the fingerprints are identical, then you've got a problem because now you have 2 scenarios that have the same fingerprint, and yet one is saying that the valid transaction is $40,000 spent at Best Buy. So the reason this could really matter is that MD5 was till somewhat recently one of the main hashes that was used, and it was broken. And in some sense, it's kind of similar to why one might want to use QKD instead of post-quantum crypto. In post-quantum crypto, you make some assumptions about what security you have, whereas here there's no assumptions. And ditto in QKD, there's no assumptions. So this is like an cryptographically assumption-free way to do fingerprinting.
Could you I guess in the first example, we could be able to reduce sort of salt.
Where salting it. Oh yeah, and I should repeat. So you're asking if salting can reduce the likelihood of collisions. Yes, but essentially if you're always going to have a problem where if the hash is 256 bits, including some, well, actually, no, the salting would not increase the size of the hash. So you're still going to have this fundamental issue of collisions. I'd have to think a little bit more of if salting like changes the background picture though.
So you argued that protocol scales well with both qubits and circuit depth. Why do you say near correction?
Yeah, good question. Akal's asking, why do we think that we need error correction given that this scales fairly well with depth and circuit gate count? And we didn't explicitly state in the paper that we definitely need error correction. In fact, there is resilience to many types of noise. If there's over rotations that are consistent, doesn't matter, it just moves unitaries to a different spot. But there's been some result, like I'm still pretty optimistic that we'll find good NISQ applications. I don't know if this is it, because as long as we need linear depth, which we would, then it means that there will be some constant depolarizing error, let's say, at every gate. There's been some results that show that essentially you're very likely to have something close to the maximally mixed state, or even if it's just a fraction, the density matrix is like fractionally the maximally mixed state, then you're in trouble because you've attenuated every outcome to be complete overlap. That said, there is plausibility that error mitigation might help here, and we have a few references in the paper of where that could help. But we also, approaching this Q2B conference, we didn't want to make any wild claims that we wanted to explicitly say that it probably needs error correction, lest some companies report about it in some non-honest ways.
And what type of verification? Is it a class you think would work well with this?
What type of error mitigation could work with this? So yeah, so one idea is it doesn't really help with the encoding stage, but there have been a few papers on how to do these swap tests better with some error mitigation protocols, including virtual distillation, which we've talked about a little bit. So that's one possibility. On the encoding circuit itself, this is not quite an error mitigation approach, but you could envision going to just like an analog system, like forget about what gates you've tuned up on AQT, just quench it with the Hamiltonian that you can parameterize easily. And in that setting, you don't really think anymore in terms of like the gate counts per se. You just think about it in terms of like the runtime of like how long did I quench for? And if it's time dependent quench, I guess it's not really quench, how long did I simulate for? So in some sense, I think of that as error mitigating in the same way that Misha Lugan's lab at Harvard thinks about having quantum advantage in their system, even though they don't apply gates. So maybe that's a possibility too. Any questions online? Well, I'll stick around here, but thank you so much for your time. And again, it's a pleasure to be here. If you're ever in Chicago, feel free to visit our office. We share it with the Obama Foundation. So some of us recently met Barack and Michelle in the elevators. I think he wasn't around while you were there, but next time. Yeah, but and you know where we're on Harper Court. But yeah, we love AQT and happy to keep working with you guys any way we can. Some of you may know that we have the SuperStack software that integrates very deeply with Qtrol, and I think we should do more demos for you at some point.
Thank you.
Thanks.